Hi everybody. Welcome to the first of several lectures on the idea of force, including the basic ideas around Newton's laws of motion, friction, and later on something about pressure. So to begin with, to talk about forces, the stuff that makes things accelerate, we first have to talk about Newton and Newton's laws of motion. Isaac Newton is probably one of the most important people that have ever existed in the history of physics. In fact, the physics that we do here is often referred to as Newtonian physics. Because Isaac Newton, to say the least, was a smart guy. At the age of around 23 years old, he was a full professor at Cambridge University, and they had to close the university because of an outbreak of plague, which happened quite often back then. And so during a lot of these closures, he worked on a lot of different things. And in terms of physics, he came up with his laws of motion, his universal law of gravitation. He discovered that white light was made up of multiple colors that all blended together. And he invented calculus. Yes, Isaac Newton was one of the inventors of the mathematics of calculus. So later on when you take calculus, you have Newton to blame. But again, a very brilliant person in terms of when it comes to physics itself. And his laws of motion really were what established sort of the ground rules of physics itself. So Newton's laws of motion center around the idea of force. And basically, in simplest terms, a force is basically a push or a pull. Okay? But there are a lot of ways that you can push and pull things. So to begin with, we'll talk about Newton's first law of motion, called the law of inertia. Now, this isn't 100% Newton's law. Galileo actually introduced the idea of inertia and a little bit of Newton's first law, but Newton sort of took it a step forward. So the law says this: an object at rest remains at rest, and an object in constant straight line motion remains in constant straight line motion unless acted upon by an external force. Now, let's sort of break this law down and see where it works. So in this example here, I have a 50 kilogram crate, and it is clearly sitting here at rest. It has a speed of 0. Now, there is no way for me to change this state of rest without the application of force. Okay? Now you might think, well, if I remove the ground, okay? But if you remove the ground, then this force called gravity will take over and change its state of rest. So it is no possible way to actually do that. And Galileo really thought that up. Okay? But it was Newton that sort of took it a step farther. In order to change this from a state of rest to a state of motion, I'm going to have to apply a force. I'm going to have my little guy do that. Apply a force for a moment here. And as you can see, it starts to move. And it's getting faster and faster and faster. But now if I remove that force, notice this crate continues on at a very constant straight line motion. In other words, a constant velocity. And now there is no physical way to change that. I can't speed it up, slow it down, change its direction, do anything about its motion without the application of force. And that was the big leap that Newton took. Basically what Newton was saying is that when it came to the idea of force, being at rest and being in constant straight line motion are exactly the same thing. And that's what we're going to find out as we do things here. But what about this word inertia? What does it really mean? Well, it's actually a hard word to really understand in terms of physics. The way it's found sort of best to describe it is a tendency for an object to remain at rest or in motion, or an object's resistance to any changes in its rest or motion. Now, a lot of this is very much related to the idea of mass, and that's what Galileo first sort of talked about. Objects with very large masses have a tendency to remain in their state of rest or motion, and it's very difficult to change that. Objects with smaller masses, a little bit easier sometimes to change their state of rest or motion. So inertia can often be related to an object's mass. But it also again has to do with that rest or motion and how resistant that object is to changing whatever it is. Let's look at a quick video example of the idea of inertia. In this demonstration, you'll see that there are a set of pennies on top of this hoop directly over this glass jar. Now the trick is to get all the pennies into the jar
but you can't touch the pennies or the jar. You can only touch the hoop. Okay, now ready? Watch carefully. There they go. So why did this work? Well, as you can see here, the pennies are directly over the opening of the jar. Now the trick is you have to come from the inside of the hoop, because when you do that, when you hit this, it flexes the hoop downward. Now the pennies are at rest, and the idea of inertia says objects want to remain either at rest or in motion. So the pennies will want to remain at rest. So when we hit the hoop from the inside, the hoop flexes down and gets out of the way of the pennies. The pennies just hover for a split second of time before gravity takes over, dropping them straight down. Now, let's watch that again, this time in slow motion.
So let's look more clearly at what happened in this little penny experiment. We have our pennies sitting on top of our hoop. And notice they're directly over the opening of the glass. That was kind of important to the whole thing. Now, the pennies are at rest, and based on the idea of inertia, that's kind of how they want to remain, at rest. Now, what happened, if you notice in the video, is that we had to hit the hoop from the inside. Because when you hit the hoop from the inside, the hoop, because it is flexible, flexes downward a little bit. And what that does is just for an instant separates the hoop from the pennies themselves. Now, because the pennies were at rest, they want to stay that way, and they stay that way just for a fraction of time. In fact, just enough time to get that hoop completely out of the way. And now that the hoop is out of the way, an external force, gravity, takes over. As we all know, gravity only acts one way, straight down. And because the pennies have very little inertia, very little resistance to change in motion, they easily drop straight down into the jar. And so that's why that trick sort of works so well. Now, had we hit the hoop from the outside, that would have caused the hoop to flex upward, which would have popped the pennies up in the air and gone all over the place, which would have made that trick far less interesting, but a lot more messy. Newton's second law of motion is probably one of the most important laws in all of physics. It's a little bit long-winded. It says the acceleration of an object is directly proportional to the amount of force applied to the object and inversely proportional to the object's mass. Now, that's a lot of writing to basically tell you one tiny little equation. F equals ma. Force is equal to mass times acceleration. Unbelievably important formula in the idea of physics. So, Newton's law, the F representing force, and the standard unit of force is a capital N. Guess what it's for? The Newton, yes. All forces are measured in the units of newtons. M represents mass in kilograms. Standard unit of mass is in the kilogram. And A representing acceleration, which is still in meters per second squared. Now, what that says is that it only takes 1 Newton of force to accelerate 1 kilogram of mass at a rate of 1 meter per second squared. But now let's look more specifically at what Newton was saying with this law. Let's break it down. Newton's second law of motion begins with the fact that the acceleration of an object is directly proportional to the amount of force applied. Now, for example, I have a 50 kilogram crate here, and I'm going to apply 50 newtons of force to it. Now, when you do that, the object starts to accelerate. And you'll see it has a very low acceleration, but its velocity is increasing because it is accelerating. However, if I double the amount of force applied, notice that that doubles the acceleration, and the rate of increase of velocity is even greater. So directly proportional means whatever I do to one, I do to the other. So if the acceleration is directly proportional to the force, then if I double one, I must double the other. The other part of Newton's second law of motion says that the acceleration of an object is inversely proportional to the amount of mass. Now in this case, I have doubled the mass, again starting off with 50 newtons of force. You'll notice now that the acceleration is a much lower rate, and in fact it is 1/2 of what it was before. So inversely proportional means if one object then goes up, then the other goes down by an equal amount. So, again, to review, if I hold the mass of an object constant and I double the amount of force applied to it, the acceleration will double. They are directly proportional. If I were to cut the force by 1/3, the acceleration would cut by 1/3. Directly proportional. Whatever happens to one happens to the other. However, if force is held constant and I change the amount of mass I apply it to, in other words, if I double the mass, the acceleration is cut in half. Inversely proportional. I invert it. If I were to cut the mass by 1/3, the acceleration would triple. Inversely proportional. And that's basically what Newton's second law is saying. Now there's an important relationship that comes from this second law concerning something called weight. Now weight is a force and it is based on mass and acceleration. So weight is measured in newtons. It is a force. In the English system we use the term pounds. So it is based on an object's mass, but it's based on a very specific acceleration, the acceleration of gravity, okay, which we already know is also measured in meters per second squared. Now, very important idea is that weight is not mass. They are not the same. Your mass stays the same everywhere you go in the universe, but your weight will always change depending on the effects of gravity. Now, we can often use Newton's second law of motion in combination with what we've learned back with linear motion. So, for example, let's say our mover here needs to move a 50-kilogram crate and has the ability to apply 10 newtons of continual force on it. For now, we're going to ignore things like air resistance, friction, things that will get in the way. And the idea is that in 20 seconds, how far can this person move it, starting from rest? Okay. Now, if we try to just do this with linear motion, we would say, okay, I have an initial velocity of 0. I have a time of 20 seconds, but I don't have any other information. In other words, I don't have enough information in order to find what I'm looking for. And back in motion, we saw that one of the keys to everything is knowing acceleration, and it always will be. But now I know force and mass. So using Newton's second law, F equals ma, well, I have 10 newtons of force acting continually on 50 kilograms of mass. So I will have a constant acceleration of 0.2 meters per second squared. There's my very important acceleration number. Now that I know that, along with time and initial velocity, I can go back to my motion equations using my displacement equation. Starting from rest, I know my acceleration for 20 seconds. And now I know that I can move this 40 meters, or a person can move this 40 meters in that 20 seconds. Not too bad, isn't it? So now we have a new way of determining acceleration that doesn't always require motion. Let's look at another example. This one, someone's driving down the road at 30 meters per second. Let's say texting. Don't text and drive. And because they're texting, they don't notice that some strange person has built a large brick wall in the middle of the road. And so they go crashing into it. Now, of course, when you crash into a wall, you're going to come to a stop. So knowing that the initial velocity is 30, we can assume that the final velocity will go down to 0. Now, you might be wondering, well, what is this 50 centimeter displacement? Well, from the moment the car touches the wall, let's say the front end crushes in 50 centimeters before the car comes to a full stop. In other words, that 50 centimeters is when the force is applied, when the acceleration occurs. Now, the idea is, well, what is the force of impact on this 500 kilogram car? Well, to get force, we need acceleration. What a surprise. Well, we have initial velocity, final velocity, and displacement. We don't have time. So now let's render our time unknown equation. EF squared, BO squared, plus 2AX. Final 0. Initial is 30. We don't know the acceleration. And we know a displacement of 0.5 meters. 50 centimeters is 0.5 meters. Always convert. Squared is 900. 0.5 times 2 is 1. And so you end up with an acceleration of negative 900 meters per second squared. Wow, that's a huge acceleration. Basically, you're changing your velocity by 900 meters per second every second. It's a massive acceleration. Now, knowing that acceleration on a 500 kilogram car gives you negative 450,000 newtons. Oh, so what does that mean? Force must be a vector. It has direction, positive or negative. And you think about, to stop a forward or positively moving car would require a negative force. And in this case, a really big negative force. So force and acceleration, they're always going to be in the same direction. Notice the acceleration was negative and so was the force. That's an important concept to remember. One last quick example. A little baseball game. So we got a pitcher who's holding a 0.2 kilogram ball, throws it so it reaches the batter at 30 meters per second. The batter swings, makes contact with the ball for 0.3 seconds, line driving it back the other way at 40 meters per second. And we want to know the force at which the bat hits the ball. Okay? Well, of course, we need that acceleration. All right, well, we have initial velocity, final velocity, time. Should be easy enough, right? Our first equation in motion, Vf equals Vo plus At. Oh, be careful now. You see, the ball was pitched in at 30, and if we call that positive, that means that 40 must be negative. Watch your vectors. Always watch your vectors. So the final velocity is not 40, it's negative 40. And think about it. Because that ball had to go from 30 down to 0, because we're going to change directions, and we always got to stop before we change directions, and then from 0 up to 40 the other way. That's a change of 70 the other way, not 10. Very common mistake. So when I subtract 30 from each side, I get negative 70, as I should, a change of 70 meters per second the other way, which gives an acceleration of negative 233 1/3 meters per second squared. Now, coming up to the force, well, the mass of the ball is 0.2. Acceleration, negative 233.3. Gives a force of negative 46.7 newtons. A lot less than a car crash, right? And again, you'll notice that because the person is swinging in the negative direction, the force is applied in the negative direction, as is the acceleration. So it all matches up what we're seeing. And that's basically how Newton's second law works. Newton's third law of motion, called the law of action-reaction, says that for every action there is an equal and opposite reaction. It is probably one of the most misunderstood of Newton's laws of motion. So basically, here's the idea. Let's say you get really, really mad one day and you go up and you decide to punch the wall as hard as you can and you break the bones in your hand. Now, if you think about it, when you hit the wall had to hit you back with the exact same force in the opposite direction. Because in order to break bones in your hand, the force has to be driven into your hand. So if you drive a force into the wall must return the exact same force back to your hand. And that's basically what action-reaction says. That if you were to take a glass and hit it with a hammer, you'd get the exact same effect if you turn around and held the hammer still and smashed the glass against it. Okay, the forces are always equal but opposite. And we'll see later on how that you can apply a force to something, it's applying the same force back, but yet you can move an object. It would almost seem like that wouldn't work. We'll see that later on. So that's basically Newton's laws of motion. These three laws will guide almost everything that we do here in physics. Okay, very, very important laws. So that's it for today. See you next time.